All right, hello everyone, and thank you again for attending this next free training webinar for video evidence. This is the third month in the series of hosting these once-a-month training webinars, and this month's focus will be on converting video, considerations when dealing with transcoding video, codecs, and validation methods to ensure that we aren't affecting video frames when performing these kinds of conversions. So this is a relatively fundamental aspect of handling video evidence. So it's going to be a very helpful webinar for those of you who are new in this field. And for those of you who have been in this field for a while, I hope that we can still touch on some things that will assist you in validating your results. The entire purpose of this webinar is to address the fundamental problem that CCTV video contains proprietary structures that can generally not be played in standard video players. We don't receive files like a .mp4 or a .avi file traditionally when dealing with these DVR formats. Instead, we receive things like a .dat file, or a .drv file, or a .irf file, and we can't simply double-click on those and play them in common standard video players like VLC or Windows Media Player or QuickTime. So the solution to that problem is to convert the video from its proprietary structure into a new format that can be played. But there are some limitations and complications with that base solution. And so for this lecture, we're going to cover what happens when those files are being converted, how to ensure that we don't have any quality loss when that's important, how to ensure that the output is playable in those standard players, because there are limitations with what those particular players can handle, how to validate that we have no quality loss, and complications with various technologies. That last slide talking about those complications is something that we run into all the time. I still tend to scratch my head sometimes when I encounter various complications. So we'll focus on a very kind of high level understanding of those types of complications. To get to the bottom of this, we're going to start from the very beginning about how these files are organized. All computer files are binary in nature. In other words, they are a combination of a bunch of ones and zeros that make up the various files on your computer. Video files are no different. When a video file is being read by a player, what happens is the player identifies the codec that is necessary to play back the file. And you can think of a codec like a language that reads these ones and zeros. So just like when I read a book in English and I can understand all the English words, I can get meaning from that book and understand what it means. If, though, I were to speak only something like German, I might catch a word here and there and understand some of the pieces of meaning, but miss a lot of the rest of the book. But if, for example, I was Japanese, I might not understand a single word in the entire book. So in the same way, codecs are going to read through these ones and zeros, interpret them as with a meaning, like images or the way that the compression is working, be able to display that image on screen. And if we're using the correct codec, then generally we're going to get accurate images displayed on screen. But if we use the wrong codec, we'll encounter some very interesting issues. Sometimes the file won't play at all. Other times we'll see some very strange things, like what we'll see here. If I were to take this .264 file here and drag this .264 file into iNPUT-ACE and interrogate it by clicking on the little interrogate button here, we'll notice that iNPUT-ACE is able to play this file back, and it's identified that the video codec here is H.264. It's the most common video codec that we see today. And what you may not know if you've even been using this program for a while is that there's a button in the settings area here that will allow us to see what codec here is being used to play the video back. And iNPUT-ACE is going through an automated process to automatically identify the patterns of the ones and zeros to choose H.264 and play this file back. But we can manually override this by clicking on the drop-down here and choosing a number of other codecs. In this case, let's take a look at what happens if I force it to be read with H.263. It'll now reinterrogate the file, and when I press play, we'll see little blips of information kind of pop in here where the rest of the screen is completely black. And it's only identifying that there are 9 frames of video down here. So we can see that this is not playing the file back correctly. There's some serious limitations. We can't see any images, and even the little tiny bits of information that we do see are just square in shape and kind of technicolored. But if I go back now to my settings and I change this from H.263 back to H.264, this frame count is going to change from a value of 9 up to a value of about 1,197, and now we get full frame video motion. So that's essentially what's happening when we're reading the file at that raw binary level and letting the codec, i.e. the language, interpret those ones and zeros in a way that in this case is accurate with H.264, but if another codec were to read it, we would get serious errors. Those ones and zeros can be read in a bunch of different ways. We can look at them as a long series of ones and zeros, or we can look at it in a format called hexadecimal or hex data. Hex data is a way of combining those ones and zeros into a structure that's a little bit easier for a human to read. So before we go on to the next few slides, I'd like to spend a little bit of time giving everyone a bit of an understanding at a very fundamental level of what this hex data is. The hex data is a series of 2 digits or 2 characters that equate a byte of data. In other words, a byte is 8 ones and zeros, or 8 bits. Hopefully this will make sense to you in a second when we take a look at an actual video file at the hex level, if you aren't already familiar with what hex data is. But you can think of each of these pairs of characters being 8 zeros and ones, where 00 is the smallest value, and it's equivalent to 8 00000000. 01 would be equal to 8 of those, and it is 00000001. 67 is going to be something a little bit more complicated, as is 42 and everything else that we see throughout the rest of this structure. So let's take a quick look back at our file. Back inside of iNPUT-ACE here, I'm going to actually toggle over to one of our iframes. I'm going to skip over the description of really what these frames mean. That's going to be covered in a different lecture that's still upcoming. But I can use iNPUT-ACE to snap myself to the hex position of that exact frame of video by clicking on this file metadata dropdown and choosing hex at current position. So this has now launched a hex reader and snapped me right to the header of that particular frame. And I can use this hex reader to see a few different things, like if I want to highlight one of these bytes of data, the hex value here of 00, I can look over at the binary 8-bit value, and it will show me that it is equal to 0000000000. I can also look at another representation of that, which is the integer value for what that is equal to. So there's a lot of different things kind of going on at play here. We have the raw essence of this file, the raw nature of this file is really a bunch of zeros and ones. This way of reading it is showing me a 2-character value that takes 8 of those digits and correlates that to a 2-character value. And then we have another way of looking at it over here, which is an ASCII text representation of the same thing. So for example, the letter H would be represented as 68 in hex, and at the binary value that is 011010000. The reason that we're looking at it in hex like this is that it is extremely difficult for a human to read a large number of zeros and ones and make any sense of it. Now, it's still not necessarily easy to see it in this way and make sense of it, but it's certainly a lot easier than looking at it as a combination of zeros and ones. And you will see patterns that begin to come out, like looking at the header for an iframe, or rather, I should say, a header for a NAL unit in this H.264 format of 00000167, and we see that repeating in a lot of these typical formats of H.264. There's a few other things in here that I'm going to point out just roughly. I'm not going to go into too much detail into what this really means, but let's take a look at one additional characteristic of this. By taking my file here, I'm actually going to drag in another file, or rather the same file, back into iNPUT-ACE. Let's view this where we're pulling out this timestamp information right here. And we can see that that timestamp information, if I were to snap back to that frame again, I can click on my file metadata dropdown, choose my hex at current position. That's snapping me over here to the header of that frame. Oops, excuse me, the header of that frame. And right before the header of that frame is a series of characters right here that are a format that is encoded in the file that equates to the timestamp. Another way of saying that is this little string of data here that comes before the header of my file is the timestamp that is encoded in the file. This is the most easy way that a timestamp is encoded. There are a lot more complicated ways, but it's lucky when we see this kind of way because we can read it quite easily. we can look at the value of 0D, which is the binary value of 00001101, or the integer value of 13. So in other words, the zeros and ones in the file are really equal to a value of 13. And if we look back here on our video, the 13 we see clearly right here is the year in the file. And if we go to the next value of 07, that is a value of 00000111, and it is an integer value of 7, which is equal to the month. The next value, I'll give you one guess. It's a hex of 16, which is equal to an integer value of 22, and we can see that that is the day. And the rest of the three over here are going to be equal to the time. So we have 13, 44, 23. So again, we're looking over here at the integer representation of that, and we can see that we have 13 followed by a value of 44 followed by a value of 23, which is equal to our time on this particular frame. So I had a quick question come in that was asking what the different offsets mean at the top of the file. So I believe what you're referring to is the offset that's listed over here on the left-hand side. And that offset is a hexadecimal representation of where in the file that is equal to. So another way of saying that is the POS value that we see here with an iNPUT-ACE is referring to the binary position where this frame exists in the file. So how many bytes into the file do we exist? It is 134,720 bytes into the file. And if we look at what that is equal to over on the hex side, that binary value, or excuse me, that decimal value is going to be equal to this hexadecimal value over here. So another way of looking at a numerical position for the offset into the file. So moving on real quick here, I hope that makes sense. And I do see a couple questions coming in. I'll readdress those here later on. I'm not quite sure I see what is being asked here. So if you can re-ask the question that's asking about the top of the file where it says offset, please re-ask the question and I'll come back to re-answer that here later on. Okay, so hopefully we have a bit of an understanding now of how this hexadecimal data works in conjunction with the binary values over here. And again, we have the integer values that equate to each of these individual bytes, and we can even see a ASCII representation of what that equates to. So there's a lot of different ways of reading these ones and zeros in a bunch of different ways that can kind of make sense to us as humans, and a computer is going to read through this linearly very, very, very quickly. And it's going to be making decisions about interpreting those ones and zeros as visual information when we read those ones and zeros as something like H.264 data. That's the real takeaway from this. Before going too much further, I want to take a quick second to talk about a file's hash. It's another technical way that we can look at a file by creating an understanding of a unique signature for that file. So just like a fingerprint can uniquely identify a human, a file hash can uniquely identify a computer file. So two files that have the same hash are the same file. I'm not going to go into the weeds of some of the limitations of MD5 hashing on very fringe edge cases. So maybe we'll address that in another webinar, but I'm going to look at this as a more high level. So what a file hash is a string of characters that uniquely identify a file. The way that a file receives its hash is by running through an algorithm that's a mathematical calculation of all those ones and zeros, and it essentially takes all those ones and zeros, it performs a bunch of math on them, and we're going to get a unique signature for a file. Let's take a quick look at our file here that we're looking at. When it's being loaded into iNPUT-ACE, we see a file hash right here for the file, and the file hash for this in MD5 is BD, A8, etc., all the way through the file. So if I were to take this video file, and I were to email it to someone, and I were to then upload it to Dropbox, and then someone were to download it from Dropbox, and then that file were to get put onto a thumb drive and sent to another computer, and then 5 years later, someone took the resulting file and ran it through another MD5 hash, as long as we haven't changed any of those ones and zeros, we're going to end up having the exact same file hash. So let's take a quick look at that. I'm going to bring up a Notepad document here, and I'm going to right-click on this file hash here, and then I'm going to choose my Control-C option to copy that. And then I'm going to go back into my Notepad here, and I'm going to say Control-V to, Control-C to copy and Control-V to paste that. And I now have my MD5 file hash listed over here in a Notepad document. If I go back over to this file and I make a duplicate of this by Control-C to copy and Control-V to paste again, I now have another file. It's the same exact size as my previous file, and I'm going to rename this file, and I'm going to call it something new. And I'm going to give it the extension, extensions don't matter. So I now have a brand new file. I've changed its name, I've changed its extension, and if I drag that file into iNPUT-ACE and I load it, we should see that everything is going to appear the same. All the metadata appears the same, it plays the same, and I've even received a file hash, and if I Control-C copy that and then paste that into my document, we'll notice that it has the exact same file hash as my previous file. So changing a file's name isn't changing anything about that file at all. However, if I take that file and I bring it into that hex reader over here, and I change any single bit of data, I change any 1 or any 0 in the entire file, it will change the entire hash. So let's take a look at that. I'm going to go down maybe to the somewhere into my file. Let's take a look at this area right here. I'm randomly in the file, and I've got a value of 0, 0, which again is equal to 0, 0, 0, 0, 0, 0, 0. And I'm going to manually override that by just simply typing in 0, 1. So what I've done is changed a single bit in the file. I've changed what was a 0 right here to a 1, and I've changed nothing else about the file. So I'm going to save this file now, and we should see that I have a new file here. It's the exact same size as the other files, but now when I drag this file into iNPUT-ACE and I interrogate it, we'll see that my file hash right here is completely different. So Control-C to copy, Control-V to paste, and the entire signature is different. So changing just a single bit of data is going to completely change the file hash. The reason that I wanted to go over this is we're going to look at changing a file away from its current structure into a new structure and the kinds of statements that we can make about ensuring that we don't change the nature of that data. The reason that we need to change files, again, going back to the quick explanation on slide 1, is that proprietary video files are unable to be played with standard video players, so often they need to be converted. That conversion is going to change the file hash. So we are actually changing a file which may have forensic implications when testifying, or when someone asks the question, did you change that data? Did you manipulate that data? We are not unable to say that we have not changed the 1s and 0s in the file, but is that really what we necessarily care about? So to get to that, let's take a look at the way that standard players are going to read a video file. We already ran an entire 1-hour webinar on this exact topic, so I'm not going to go into too much detail on this. But if you'd like to get a more thorough explanation for how containers work and how the various video players are reading those containers, I recommend you check out our YouTube page. We already have a full hour-long webinar devoted to this exact topic. The takeaway from that is going to be that these video files require a container when they're going to be played in a standard player by default. So let's take a quick look at that. I go back to my file here. I can't simply double-click on this and have it play with a standard player. I can't open this with something like Windows Media Player and say, play that .264 file. It's going to say, I can't read this because it's an unknown extension. Do you want to try to keep playing it? Yeah, go ahead. And it can't do it. So if I were to simply rename this file to something that has an extension like .mp4, does that change the file in any way that is going to change the way that a player is going to play this file? And the answer is no. If I were to try to open this again with Windows Media Player, even though it got the extension MP4, it says I can't play this. Because again, looking at that hash example that we just did, changing a file's name or changing a file's extension is not changing any of the 1s and 0s in the file. So this file with a .mp4 is going to be the exact same file as it was when it was a .264 file. So still, common players like Windows Media Player and VLC will be unable to read them. So one quick takeaway here is that proprietary video isn't exactly always proprietary. It just doesn't have a container. So in the case of our .264 file, we can see that it is a common H.264 codec, and when iNPUT-ACE is reading it at that raw binary level, it's reading right through those 1s and 0s, interpreting them and displaying them on screen. But again, there is no container here, so we can't play this inside of a standard player. So what we can do in some cases is just simply give the file a container. So let's do this. Let's take that .264 file and let's put a container around it. That concept is called rewrapping. So back in iNPUT-ACE here, I'm going to do this very quickly. We're going to toggle over to our workflow tab, and I'm going to make a very quick workflow that's going to take my original file, this original .264 file here, and we're going to rewrap it into an MP4 output. To do that, I'm simply going to click over here on my MP4 option on the far right-hand side. I'm going to choose an output location. I'm going to name my file simply rewrap. And the important part here is to change my transcode video setting to same as input. This is the option right here that's going to perform that process of rewrapping the file. Same as input or rewrapping, they mean the same thing. We'll come and talk about this word transcode here later on in the lecture. One last thing I'm going to do here is I'm going to check this checkbox to send the outputs to the file list. All that means is once this workflow is done and we've processed our file to same as input MP4, that the results are going to pop back over here in my file list. So to perform this workflow, I'm going to simply connect my file to my output. I'm going to press the execute button. It's that quick. The file's already been rewrapped, and here's the result. And we can see that when I interrogate that file, everything is going to look pretty much the same. We have the same number of frames. We have the same frame rate that was by default set on the other file. We have the same codec, the same pixel format. All of the metadata is basically the same over here. But we will notice that our file hash, if I were to Control-C to copy that and then paste that over here, let me delete out the last example. This was our original file hash for the .264 file, and the new MP4 file is completely different. So we have, in fact, changed the ones and zeros when we performed this process, and we can look at that. If we open up our file metadata here and launch this file in our hex reader, we can see that the entire beginning of the file has different data than the original .264 file is. So yes, we've changed this file. In fact, we can even see that the file size is a little bit different. The rewrapped file is 3.83 meg, and my original .264 file is 3.93 meg. So we've changed the size of the file, we've changed the number of ones and zeros, we've even changed what those ones and zeros look like in a lot of cases. So yes, we have changed the file. But is that really what we actually care about? Do I care about changing the entire file's hash, or do I really care about ensuring that I don't change the image data for every single one of these images? And I'm going to argue that that's the part that we don't care about. I want to ensure that I don't change any of the actual visual information on this file. So how can we prove that this rewrapping process hasn't changed that? Well, there's a few different ways to do that. So what I'm going to do is I'm going to start by looking at the hex level here. Let's just go to the first instance of one of these frames, so I can identify it on both the rewrapped file and on my .264 file. And if we look here, I'm right now on the very first frame of 144.26. So back a frame, we're on 25. Forward a frame, we're now on 26. So right now, if I snap myself to the hex at the current position of this frame, we'll see right here that there's the beginning of that frame. Now let's do the same thing over here in my .264 file. I was on the time, oh, excuse me, what time was I on there? I was at 144. I'm talking too quickly. I was at 144.26. So back over here on my .264 file, I'm going to go to 144.26. Backwards to here. I've got backwards is 25, forwards is 26. And if I open up my file metadata at that current position, we'll see that we now have that frame highlighted right here. So this is, again, the header to start that frame, but what I really care about is the actual video information that really starts back over here. So after the header, we're seeing FE1450, etc. And I'm going to actually copy that data, and I'm just going to paste it in this document. Let's overwrite all this file hash information. And I've pasted the beginning of the actual frame of data. And back over on my rewrap file, we're going to see that we have the same process. We have FE14, etc., all the way through the frame. And all of that is going to line up exactly, meaning we haven't changed any of the raw ones and zeros all the way through the actual frame. And I've only selected a very small portion of that. The entire process all the way down here would line up. So we haven't changed the actual ones and zeros for any one of these video frames, meaning when we display it, when reading it with H.264, it's going to decode to the exact same frame. So we haven't changed anything about the actual frames themselves. Here's another very quick way of looking at that. I'm going to go back to my workflow tab, and I'm going to take my original .264 file and my rewrapped MP4 file, and I'm going to write them both to a bitmap image sequence. So I've made a bitmap output node. I'm going to go in my output folder here, and let's make a new folder for my original file. And I'm going to save a whole bunch of bitmap images for every frame of video called original. And then I'm going to make another bitmap output node, and I'm going to call this one rewrap. And it's going to go into a different folder that we're just going to call my rewrapped file. And I'm going to give my file name rewrap. So now I'm going to send my original file to that bitmap output and my rewrap file to this bitmap output. And when I press execute now, it's going to very quickly go through and extract out a sequence of bitmap images into my rewrap folder and into my output folder. I'm going to manually or just randomly select a random bitmap. Let's use this one here, 00311.bmp. Let's bring that image into iNPUT-ACE. So what I now am seeing is a full bitmap image representation of the frame at 311. Let's do the same thing on my original at 311, which is right here, 311, and I'm bringing that bitmap image in. Now, because both of these files contain the exact same visual information for the frames, when I write them out to a bitmap image sequence, the bitmaps are going to be exactly the same. And in fact, we can prove that by looking at the file hash of the frame at 311. Gives us this file hash right here. I'm going to copy that and paste that into my Notepad document. And if we look at the other bitmap, it's going to give me the exact same hash. So we can prove that every single bitmap has the same hash, meaning my rewrapped file is going to have the exact same frames as my original file. Now, this is a very time-consuming way of doing this proof. There's a bunch of other ways that we can do this as well. We can do difference filters. We can do structural similarity indexes. We can do MMS. We can do a whole bunch of different ways of proving the same thing. One of my personal favorites for doing this proof is going to be another option here on our workflow tab. We have another node over here that will calculate the frame hash of every single frame of data in a file. So essentially, similar to the way that this bitmap option is calculating the hash of a single frame of the video, we're going to do that for every single frame of video from both of these files, put it into a spreadsheet, and compare every frame hash from this file and every frame hash from this file. To do that, I'm going to open up my settings. I'm going to choose a simple output name. We're going to call this frame hash. I'll put it here in my outputs folder, press save, and then execute this workflow. Now in my output folder over here, I am going to see a new framehash.csv. And when I open this up, we'll see that every single frame of video in my original file and in my rewrap file has the exact same hash all the way through the file, proving that every single frame is exactly the same when it's being decoded for every frame of video throughout the entire sequence. So this is a really quick way of doing that. And we're going to use this again later when we talk about other options for performing this kind of conversion. So rewrapping is very easy. It's very fast. It's going to create a lossless version of the frames. So why would we not just simply rewrap every single time? Well, rewrapping has a serious limitation, and the limitation is that it's only going to work when we're sending an original file directly through to an output. And what I mean by that is we oftentimes are going to want to perform slightly more complicated conversions than simply taking an original file and turning it into an MP4 file. So in this case, what we had done to start off this example was choose same as input as my transcode option. And then in my output folder here, we named the file something like rewrap. I'm going to call this rewrap new. And this process will work if I connect my original file directly to the node. However, sometimes I might want to do things that are a little bit more advanced. Like I might want to put that file into a canvas editor to combine multiple camera views all into the same plane. I might want to do something like decimating the frames to get rid of duplicate images. I might want to do enhancement techniques. There's all sorts of things that I might want to do to the file, including something simple like cropping. So let's just choose a simple crop right now. And when I connect my file to a crop node and I open up the crop settings, if I were to crop out, for example, the pool over here in the background, what I've now done is I've changed that file. So the file was a combination of a bunch of ones and zeros. I'm now selecting a region of that image, which is going to basically change the ones and zeros in the file. And now when I try to connect this to a rewrap, that is not going to work. And if we see when we press the execute button, it's going to pop up an error message 101. Users that have iNPUT-ACE can go to the user manual and read what that error message says, but it's basically explaining that you can't use the option same as input when you have any processing nodes in the workflow. So this is a common error that will pop up when people try to do this process. And the reason for it is the rewrapping option with MP4 with anything will only work when an original file is connected directly to the output. If we do anything else in between, we're changing the ones and zeros, and the logic no longer makes any sense. Because essentially what we've tried to do here is say, take these ones and zeros, change them in this way, but then copy the original ones and zeros into my output. And that just doesn't make logical sense, so it fails. So that's a pretty big limitation. So what other options might we have to do these kinds of conversions if what we really care about is ensuring that we don't change any of the picture values? Yes, there are other options. And the other options are a process of performing a lossless transcode. So unlike rewrap, where what rewrap is really doing is copying all the ones and zeros directly from the original file into the output, the lossless transcoding is a way of decoding a file, reading all of its ones and zeros, and then re-encoding them in a new way. So we will be changing how the files are represented at the binary level, but the goal here is that even though we're changing the codec, we're changing the language in which the file is going to be read, we're going to ensure that we're always going to display the same frame. So what I'm looking at over here in this image is a very simplified version of this. So imagine we have a file that is the value 1 plus 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 1. That file might be large. I mean, it takes a lot of characters to represent that, right? 1, 2, 3, 4, 5, a lot of size to represent this file. But if we were to decode this with a codec that understands the concept of plus, when it decodes 1 plus 1 plus 1, etc., it's going to get a value of 10. So in this analogy, this is basically our file, and this is basically what that file looks like when it's being displayed on screen. To simplify that even further, let's say that this is an image, and this is what the image looks like when it's displayed on screen. So inside of the file, we have a large set of data. When we display that after being decoded, it's going to show a value of 10. Well, here's another way of encoding the file. We could have a file with a concept of 5 times 2, and if we decode that with a codec that can understand the concept of times, it's still going to decode a 10. So if we're displaying 10 on screen here, and we're displaying 10 on screen here, those frames are exactly the same. But it takes a lot larger of a file size to represent this than it does to represent this. Even further, we could encode a file with a concept of 10 that when it gets read, just simply decodes the 10 into a concept of 10. And we're going to now have 3 different ways of representing 10 with 3 different kinds of files. So this is like 3 different codecs that all produce a concept of 10. And if our original file looks anything like one of these, we can decode it to a 10, and then we can re-encode it to any one of these. So I could take a file that is 1 plus 1 plus 1 plus 1, etc., and I could transcode it, which is a concept of decoding to 10 and then re-encoding to something else. So converting the file from this into this. That's a concept of transcoding, decoding the file, encoding the file. We have now 3 main options that I want to focus on. We have rewrapping, which I've already talked about. We have uncompressed, which we're going to look into now, and we have lossless H.264, which is another form of lossless transcoding. There are many other ones, but we're going to focus on these 3 primary options. So before we look at which option is best, let's take a look at what those look like inside of iNPUT-ACE here. So I'm going to clean out my file list. I'm going to delete out everything except for that original file, and I'm going to wipe clear my workflow tab. And let's take a look at 2 additional options. So we've already looked at the rewrapping option. Now let's look at uncompressed AVI. So I can do that by simply clicking on my AVI output. It's going to pre-fill in uncompressed as my default settings here. And in my output folder now, I'm going to make a file called uncompressed. Just like before, I'm going to send my outputs to the file list when it's done processing. And I'm also going to create a second output, which is my output to MP4. And I'm going to leave the default settings for this now. This is going to be a lossless form of H.264. And I'm going to name this one here lossless H.264. So we now have 2 output nodes, and I can take my file, I can connect it to my uncompressed AVI, and I can also connect it to my output to MP4. And when I process this, I'm actually going to check this checkbox here to send my outputs to the file list. When I process this here, we're now going to get 2 resulting files. The uncompressed one gets done first, and then my lossless H.264 gets done next. So we now have two new files. They're very different in size. So if we look at my original file first, we see that it is 3.93 megabytes in size. My uncompressed is significantly larger. It is now all the way up to 144 megabytes in size. And my lossless H.264 is only 16 megabytes in size. So there's a pretty significant size increase on our uncompressed file compared to the other options. But just like in our example of having a 1 plus 1 plus 1, etc., decoding to 10, all three of these files are exactly the same picture values on their frames. And again, we can prove that by using our frame hash CSV option to take my original file, my uncompressed AVI, and my lossless H.264, bringing them into this frame hash option here. And I'm going to say frame hash comparison. And when we run this now, we're going to get a comparison of all three of those different files all lined up in my frame hash. And it's going to show me that I have the same hash all the way through the report for my original file, my uncompressed, and my lossless H.264. So we now have another option for doing this, but the benefit of my H.264 and my uncompressed options is that those options are going to work when I apply additional nodes into my workflow. So for example, if I were to apply a filter to crop either one of these, like my uncompressed or my lossless H.264, once I crop out the region of interest, like the pool, for example, that will now work. So I can now send that out to a lossless H.264 output, and I'll just call this cropped. And when I run this, this option will now function accurately. So we're able to perform additional actions on any one of our inputs by sending it to a lossless transcoding option. And those transcoding options are exactly the same quality as doing a rewrap, but we did see that they are different file sizes. So if my original file is rather small at 3.93 meg, we saw that my rewrap was close to the same size, so it doesn't really increase in size at all, because again, we're not changing the ones and zeros of the frames, we're basically just copying them into a new container. But the file size gets significantly larger with uncompressed, and it's a little bit larger with lossless, but it's still in a manageable size. So which option is best between those three different concepts? Well, it's going to depend, and this really here is the crux of this presentation, is to talk about the weighted differences between which option is best, depending on what scenario we have. And there are really 5 primary factors that I'm going to focus on. It's the file size, which we've already looked at. The rewrapping is going to be the smallest, and uncompressed is going to be the biggest. The speed of conversion, which we'll talk about on the next slide. The playability of the file, and what I mean by that is how easy is it for someone to play the resulting file in common players like VLC or Windows Media Player, or importing that file into another program like a nonlinear editor, for example, or bringing it into Photoshop for doing additional enhancements. The image quality of the image itself, and this concept of, is it even possible? We've seen that it isn't actually possible to take a file and change it and then also try to rewrap it. And there are other considerations with situations where it also isn't possible for other reasons. So each of our 3 options between the rewrapping, the lossless H.264, and the uncompressed are going to have their own benefits and disadvantages. So let's take a quick look at a summary of some of those advantages and disadvantages for each of these different options. For rewrapping, it is the smallest file size, generally, in almost all cases. It's going to be the fastest in all cases. It's very easy to play in most common players like VLC, Windows Media Player, and QuickTime, assuming that we have a standard H.264 file to begin with. But it has a significant limitation that we've addressed, where it's only possible when doing direct conversions. We can't change the file in any way when doing this process. Uncompressed, on the other hand, is going to be the largest file size of these options. It's a moderate speed to create. It's moderately playable. It will be playable in something like VLC. It will be playable generally in something like QuickTime, but it won't, unfortunately, be playable in Windows Media Player. But it does have the benefit of being theoretically always possible. If we can decode the file, we should be able to transcode it to uncompressed in pretty much all cases. There are some small limitations depending on the structure of the file, which I'll talk about in the next slide. Then with lossless H.264, it has a moderate file size. It's a little bit bigger than the rewrapping, but it's still pretty small. It's got a moderate speed. It was a little bit slower than uncompressed, but not by too much. It's moderately playable. It will be playable in VLC, but unfortunately it won't be playable in Windows Media Player or in QuickTime when it is lossless. And it is also theoretically always possible. So here's some brief kind of disadvantages and benefits from these different options. And so when you're choosing an option, it really depends on what your goal is. Is your goal to play it in court? Well, does the court allow for playing the file in something like VLC? They're probably not going to have iNPUT-ACE, so they probably can't play the original file. So they're going to be stuck playing it in something like VLC or Windows Media Player. If you're forced to use Windows Media Player, you're going to be stuck with some limitations here. If you can use VLC, you now open up the door to being able to use something like Lossless H.264. So here are some extra considerations that we need to think about with this kind of thing. We have a bunch of compatibility issues, and this is something that is extremely hard to pare down into something that's deliverable to you. But what I'm going to go through is a quick summary of some of the common ones that you'll run into. You'll see this with any video technology. This isn't just an iNPUT-ACE limitation. It's a limitation across the board with video technology in general, with things simply not fitting together. For example, uncompressed PCM audio cannot exist inside of an MP4 container. So if you have an original file and that original file has video on it, maybe it's H.264 video, and it also has uncompressed audio in PCM, you cannot convert that to an MP4 container, regardless of what codec you're using. So if you're using H.264 and you're for the video, or you're using uncompressed for the video, or you're using anything for the video, if you try to keep that uncompressed audio, it will fail. It's a very common thing. We run into support questions for that kind of question all the time. And unfortunately, the only way to get around that is either to change the audio codec to something that's compatible with MP4, which will likely require then compressing it slightly using something like an AAC audio codec, or you change the container. Maybe go into an AVI file that does allow for uncompressed audio. But AVI has a limitation where it is unable to hold uncompressed RGB video. So again, there's just a bunch of these compatibility issues across the board. The color space YUV444P is not going to be compatible with Windows Media Player. It's also going to have a bunch of limitations with the AVI container as well. Also, we have limitations with things like an odd width and height of a file cannot be encoded with most forms of H.264. I'd almost go all the way to say all forms of H.264 in most cases. So what I mean by this is when a file is something like 704 pixels across by 480 pixels across, that's an even width and height, and it is compatible being encoded with H.264. But if we tried to crop that file and we cropped it down to something like 711 pixels by 241 pixels, now we have an odd width and height, and we cannot encode that with H.264. So in iNPUT-ACE, you'll see an error message. In other programs, you'll just see it outright fail. It's a very common limitation. We see it primarily when doing things like cropping, or if you're trying to resize, or if you're trying to put files into a canvas editor, putting them side by side, you'll end up seeing limitations like this. There are many more, but I want to make sure that we have time for questions at the end of this webinar, so I'm not going to go into too much additional detail. We just suggest that you kind of familiarize yourself with these as you run into them, trying to make sure that you learn these as you go. It really comes down to just experience of running into this, banging your head against the wall a little bit, and then getting familiar with these kinds of limitations. So one last consideration that I'd like to talk about here is the concept of, do we always need to be 100% lossless? And that's really coming back to the slide over here where we're talking about the various options or various factors, where we're looking at the primary factors of file size and speed of conversion and image quality. Let's take a look at that image quality option now. So previously, all of our options between the rewrapping, the lossless H.264, and the uncompressed all have the same image quality. We're going to look at another option now that may not have the same image quality, just to put another bag in your bag of tricks in case you run across scenarios where this is helpful. To do this, I'm going to take a look at another video file. It's going to be a .exe file. So when we double click on this and play it, we'll see a proprietary exe player that has a bunch of different camera views all kind of wrapped up inside the exe. But we're going to, instead of using the player here to look at the video images, because there's a bunch of limitations with this particular player, we're going to take that file, drag it directly into iNPUT-ACE, Let's interrogate the video. iNPUT-ACE has now gone through and identified all the various camera angles in the file, so we can view camera 1 kind of independently from the other camera views. And what I'd like to do right now is take a look at this real case. We're going to scrub forward here to an incident that occurs where an individual comes in with a mask, robs the teller here, and then he ultimately runs out the door and leaves the building. So if we were going to do forensic statements about things like the shape of the object, or the color of the jacket, or the pattern on the clothing, or anything to do with aspect ratio, we're probably going to be concerned with ensuring that we don't change this data in any way. We want to make sure that we keep these picture values the same. So in forensic statements, that's critical to us. However, if all we're doing is building a narrative or providing a video to the trier of fact or to an attorney or to an investigator to say, here's the incident that occurs, the individual comes in at this time, he walks up to the teller, he does these actions, he then leaves, and all we're doing is tracking him and providing a video clarifying the events in that way. It may not matter that we're exactly 100% lossless, as long as we ensure that we don't have any visual loss that changes the meaning of the video. So let's take a look at that. I'm going to make a quick subclip here, which is performed by marking an in with my I key, and then either playing through the video or kind of scrubbing through the video here. I'm just clicking my mouse and dragging, and I'm marking an O to mark an out. So I now have an in and out that are segmenting a small section of video, and I can create a subclip of that by pressing my S key to create a clip. So I now have a little clip of video right here that I can interrogate if I want to, and I can see just that small section of video. But what I'm going to do now is convert that video out to a couple different options and then compare the results side by side. Before I do that, let's actually change the frame rate of this too. I can look at the timestamp here that's being pulled out of the file, and I can count the number of frames per second. And again, this is a very general thing. For those of you who are at the LEVA conference this last week, we went into pretty deep detail on how these files contain variable refresh rates. What I'm going to look at right now is just giving a general refresh rate to this file so that it will play back in a more normal speed. To do that, I'm going to count manually, starting on this first instance of the 24th second. This will be frame 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then it changed on the 15th frame. So we have 14 frames in that 1 second. Other instances are going to have 15 frames. So if we count this one here, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, or it changed on 15 again. So this actually does change back and forth between about 14 to 15 to 16 frames per second, averaging around 15, but the two we looked at here were 14 frames per second, so let's just use that as an example. So over on my workflow tab now, what I'm going to do is create two different outputs from this little clip. One of them is going to be uncompressed, completely lossless, changing the speed to 14 frames per second. I'm going to choose my output here, and I'm going to call this my uncompressed clip. And again, I'm going to check that checkbox to send the outputs to my file list. So this output now is going to take that subclip, it's going to create an uncompressed series of frames with a frame rate changed. Then what I'm going to do is open up my MP4 output again, but instead of using the default, which is 100% lossless, in other words, there is zero additional compression, all of the pixels are exactly the same in this, I'm actually going to allow this to introduce some amount of compression. So this is now up to a value of about 20, anywhere between about a value of 2 to a value of in the mid-20s is going to be what we call visually lossless, which means that yes, there is mathematical loss. You can calculate the loss. It will be a different file hash, but visually, we're not going to be changing the nature of that video. The actions, the activity is all going to still look the same. We can even compare them side by side, and our eyes won't be able to tell the difference. So that's what we're going to take a look at now. I'm going to give this output name here. I'm going to call this a visually lossless. And I'm going to check this checkbox to send the output to my file list. So now when I combine these two, or I press my execute button, I'm going to have my results pop in. Again, uncompressed will come in first because it's a little bit faster than the visually lossless option is. And we can play this forward, and I can watch them independently and not really see any difference. Oh, I did forget to change my frame rate on this option, so excuse me for that. I'm going to go back and override this. So I'm going to go back to my workflow here. Let me delete out this visually lossless option. I'm going to delete this line. I'm going to go back into my output to MP4, and I'm going to add in my change frame rate to 14 so that it matches the same frame rate as this AVI output does. And let me just re-execute. I'm going to overwrite the file. So now I'm going to have my uncompressed clip in and my visually lossless H.264 both playing at the same frame rate. So ultimately now what I want to do is I'm going to take those two clips and I'm going to put them into another node called the canvas editor, which will take these two files and allow them to play back side by side so I can compare my uncompressed on the left with my visually lossless on the right. And I can send this now out to my uncompressed output to AVI, and I'll just change this name here to side by side. When I execute this now, what I'm going to receive is a side-by-side video that I can now look at and watch and see any differences. Now again, there is loss, so I'm not trying to use this for forensic purposes. I'm not trying to measure the suspect or say the shape of anything or address the color of anything. But if all I'm doing is presenting something at trial that allows someone to watch the events, and that's my goal, then this is another option for us. Its benefit, if we look at it, is it is extremely easy to play in most things. So my visually lossless option will play in VLC. It should play in Windows Media Player. If I say open with Windows Media Player, it will play. It should play in something like QuickTime. If I say open with QuickTime, it should play. So it will play very easily in a large number of different outputs. So going back now to our little checklist for which option is best, when looking at these 5 primary factors, the visually lossless option, which is a value of changing that slider again to introduce some compression, it's going to be a very small file size. It's going to be very quick to perform. It's going to be very playable. But now we have the limitation of the image quality being different. So to answer the question of which option is best, it really does depend on your needs. If you need the image quality to be unchanged, then you cannot use the visually lossless option. If you are okay with introducing some image quality differences for the purpose of playing in court, we will be not changing the essence of what is occurring on the video when using this visually lossless option, so it can be an option in the right circumstance because of the benefit on these other factors. Now again, you do always have the original file that you'll be going back to for forensic purposes, so it's just another option for your toolbox, and it really does just depend. Okay, so with that, I'm going to open it up to some questions. I've been seeing some roll in throughout the webinar. We're running up right on our hour here, so please, if you have additional questions, please feel free to add them. And I already see a couple that have come in. One of them was asking about what a bitmap is. And I think that will actually pair well with another question that I see here, which is asking about what uncompressed screen capture is. So I'm going to answer those two kind of simultaneously here. Back within iNPUT-ACE on the workflow tab, just going back to talk about what the question is addressing exactly. If you recall, we did an option where we had an output to bitmap where we sent an original file directly to a bitmap image sequence. What a bitmap is an image format that is a lossless image format that is essentially an uncompressed image. Now, what do I mean by uncompressed? Well, in an original file like a video file that is encoded with MPEG video like H.264, that format includes a way of reducing the storage size by removing redundancies within an image. So we're going to have a whole 1-hour webinar on this exact topic, so I'm going to give you the 30-second overview of this. But if you imagine, for example, that you have an image frame that is a white image, well, every single pixel value costs storage size to store that white image. So if we were to create a bitmap image of a white picture, it costs a lot of size. If we then create another image of the exact same thing, a bunch of white pixels, and we were to encode that to a bitmap image, we have 2 images that are both very large, and we have twice the file size. We add a 3rd image, it's going to add the same amount of size. 4th image, it gets really, really, really big. So when we look at surveillance video, we'd have a serious limitation if we encoded video in that way, because every single time that a new image is calculated, it costs storage space on the device. So when we have 8 cameras of video running 24/7 with a large number of frames per second, we have a significantly large amount of data that's trying to be stored, and it just will not work with our current hardware. So what we introduce to account for that is a form of compressing the data to remove some of the storage size by copying stuff that hasn't changed. So now in the case of the white picture example, if we had a white frame on frame 1, frame 2, if it was also going to be white, doesn't need to store all the pixel values again, because it can simply point back to the previous image and say, hey, I saw that the previous image was all white, let's just copy that. And the concept of copy that is a lot smaller than the concept of storing all of the white pixels. So that's kind of a very quick summary on how video is encoded. One of the ways that video is encoded, it's called temporal encoding. It's present in pretty much all MPEG-formed video, including H.264 video that we see. But as a byproduct of that now, when we look at our frames of video at the raw binary level, we have some frames that include all of the pixels and some frames that include a bunch of the copy that concept. And we can't look at a frame that has that copy that concept in and of itself. Those frames are called predictive frames, either P frames or B frames, and they essentially don't live independently from the other frames in the video file. So you need to have those full frames or those reference frames, but they're also referred to as intra frames or I frames. We need those full frames in order to be able to produce the other frames in the same video file. So the reason I'm giving that quick explanation here is when a video file like this original .264 file we were looking at previously, that file contains frames that are encoded that way. Some I frames that are full pictures, some P frames that are parts of pictures. They're called predictive images, P frames. And when we re-encode the file to something like a series of bitmap images, what we're doing is basically saying, take frame 1, let's decode frame 1. Let's understand what that frame looks like. We could display it on screen, but instead what we're going to do is encode that picture value to a bitmap image. So original file being decoded, image value, to then being encoded as a bitmap image. The next image might be a P frame. We're going to decode that P frame, which includes the concept of rebuilding all the pixels that are being reused from the previous image. We now have a full picture, and now we can encode that out to a full bitmap image. So now we have 2 bitmap images that are the same size. They've gone way up in file size, and now we're basically reproducing all of our image frames as bitmap images. So that concept of transcoding a video file into a bitmap image sequence consists of that basic process. The uncompressed concept, like with the uncompressed AVI, is essentially doing the exact same thing. It's taking an original video file and it's decoding that video file and re-encoding that to essentially a bitmap image sequence inside of an AVI container. You can think of it like that. So every single frame of video is now being represented with all the pixel values. So all of the concept of the P frame reducing storage size by copying data is no longer there. Instead, now it's all full images all inside of an uncompressed AVI. That's why the file size gets so dramatically larger when we look at an uncompressed AVI. Like in this case, that clip here is 156 megabytes, whereas the visually lossless version of that is only 21 megabytes. This version over here contains that form of compression. This one does not. It's essentially a bitmap image sequence. So the file size gets way, way larger. So the question is, how does this work with screen capturing? Well, when you take a proprietary player like this, exe here, and you use something to screen capture it, like one of the very common tools in this industry is using Omnivore, produced by a company called Ocean Systems. It's definitely a necessary tool in the toolbox because it allows you to capture the images displayed on screen from proprietary players. Now, I wouldn't recommend defaulting to grabbing from a proprietary player, but it's absolutely sometimes a necessary thing to do when you can't get access to that raw data in another way. So if you don't yet have Omnivore, I recommend you reach out to Ocean Systems. It's something that is definitely required in the toolbox. But the big limitation of that is the way that it works is by literally taking a picture, essentially, of what your graphics card is seeing and displaying, which means that the decoding process is being done by the proprietary player, and we don't necessarily have control over what the proprietary player is doing to display that image. Is it displaying it at the right size? Is it potentially missing images, potentially changing shapes? There was another webinar that we went over recently that goes over that concept in a lot more detail. So again, if you haven't had a chance to look at our YouTube page, I recommend watching through that webinar. You'll see some cases where these proprietary players make some serious mistakes on the file. That's not to say that screen capturing in its essence is bad. It's necessary in a lot of cases. But the way that it works is by using the player to perform that decoding process, and then taking essentially a screenshot and turning that into an uncompressed image. It's rebuilding all those pixel values by using the player to do the decoding process for you. So I hope that makes sense. I've got a couple other questions here. One of them came in asking about visually lossless. Is there a range for visually lossless? And the answer is yes. So I'm going to delete out this bitmap node here and bring back in my MP4 node. You'll notice again, by default, the value is set to 0, which is completely lossless. And visually lossless is going to range anywhere from a value of about 2 all the way up to roughly the mid-20s. And again, because this is a bit of a subjective thing, the concept of visually lossless, can we visually see a difference? That does mean that erring on the side of a lower number is going to be more likely to be undetectable. And of course, the higher numbers are going to end up being quite compressed. The value of 100 is very compressed. So I generally, when I'm intending to be visually lossless, I'm going to range anywhere from the mid-20s down. And again, going back to our slide over here, we're talking about the benefits versus the disadvantages. The more compression we add, the smaller the file. The more compression we add, generally the faster it's going to be, and it's also going to be more playable. But the image quality is going to suffer. So now we have this weighted decision to make, and if we're going to allow ourselves to introduce some image quality loss, I'm generally going to want to stay in that visually lossless spectrum, ranging from a value of about 2 to the mid-20s. So I generally will sit at around 18 to 20 to 22, because it's a nice happy medium that creates a file that is going to be playable in all of the general common players. It's going to be quite quick. It's going to produce a very small file size, and the image quality doesn't suffer that much. Again, not applicable for doing forensic statements of things like color and shape, but it might, if you deem so, it might be appropriate for doing things to present at trial when all we're doing is tracking a suspect and talking about A, B, C occurs on the video. Again, that's up to you to decide, but the option is there if you choose to use it. Okay, I'm seeing another question asking about the previous webinars. It's a person that's attending for the first time, so hello, thank you for attending. We really appreciate it. They're asking where we can access the past videos. So let me open up a new web browser here. If you go to youtube.com and you simply type in the search bar here, iNPUT-ACE, and search for that, the very first link here is our YouTube channel. There's also some additional videos by Ocean Systems, but the official iNPUT-ACE down here is the Ocean Systems ones. The official iNPUT-ACE channel that has all of iNPUT-ACE's videos, including some details in the future about the product, but right now these are mostly the training webinars. The past 2 webinars are present here. I definitely recommend watching them. And please, if you choose to, it does help us if you subscribe to the video. It will allow us to customize some things and hopefully benefit you all for making these videos a little better. In addition, if you subscribe to the videos, it will allow you to receive updates when we upload these. The current webinar, once we wrap this up, we'll be getting this online shortly, either sometime this week. So I think I'll end there. If you have any additional questions for us about anything you've seen in this webinar, please do not hesitate to contact us. Again, my contact info here, if you'd like to reach out to us, is andrew@inputace.com. You can also reach out to our general contact page here at www.inputace.com, and our email address here is info@inputace.com. So thank you again, everyone, for attending. We really appreciate it. And again, if you have any additional questions, don't hesitate to email us. Thanks again, and have a great day.